Okay, students, another major application of the calculus has to do with summing a bunch of small parts together to get a total. Um, here's an example. Let me just point it out to you. We have the curve y is equal to negative x squared plus 4. Okay, and so here's this curve. And now what I'm wanting to do is I'm wanting to find the area under the curve. Let's just say we want the area from 0 to 2. Now, as you know, this is a curve, so we'd have to sort of guesstimate what the height would be to be able to approximate it with a rectangle. Now, one thing we could do is we could divide this region into smaller parts and have rectangles that that we could use to approximate the height. So let me explain what I mean by that. I'm going to animate the screen, and uh, we're going to make more and more rectangles and find the area of each rectangle and add them together to approximate the area under this curve. So as you know, the curve is it goes up 4 and it goes to the right 2. That should be a 2 right there. 4 times 2 is 8. Okay? Well, we know the area is less than 8. Now notice I am up to 29 rectangles, and the area 5.33. Even though the numbers are going higher, it's refining. The area it's narrowing down to a certain amount, and we could use the idea of a limiting process and a summation process to be able to find the area under that curve. And that's what integral calculus is all about. Okay, so here's our function up here, here's a picture, and here's the interval that we're dealing with. You may remember the number wasn't it close to 5.33? Okay, the area under that curve. What we're going to do is, just like the last time where we had some pre-algebra concept, we had some limiting process, and then we had a formula, 2x, we can go through the same process and come up with a formula to be able to describe the area. Last time it was to be able to describe the slope of a tangent line. Now, I'll have to tell you, I should have told you before, when we work with calculus, we could go from here all the way over to there without having to go through the delta x process. Now, that involves some study, but it's really very interesting. Okay, now in this problem, we're trying to find the area under the curve. Now, what I'm going to do is just cut to the chase and let you know what we're trying to do is we're trying to find the integral from 0 to 2 of our function here, our function with respect to x. And doing integral calculus, again, I'm cutting all the way from the beginning all the way to the end, okay? We're going to get something that looks like this. Negative x cubed over 3 plus 4x. And we're going to evaluate this for the number 2 first and then 0. Now let's plug a 2 in here. Plug a 2 in there, I get negative 8 over 3 plus 8. And then if I plug a 0 in there, I just get 0. So remember, 8 over 3 is really just 24 over 3. And subtract 8 over 3. And lo and behold, we get 16 over 3, right? 16 over 3, which is 5 1/3. That's 5.33. 5.33 repeated. Now, I want you to notice how very similar it was to that number that we spoke about before. Now, this is a very powerful mathematical idea. It's called integral calculus. And what we're going to do is try to go through this step by step. Okay, the first thing we have to do is sort of, I guess you could say, draw a picture of that rectangle. and we're going to call it A sub I, which talks about the area of the ith interval here. We're going to divide this. As you know, we were dividing it into further and further values of n. N would be the number of rectangles. So remember, this was 0 and this was 2. So if I divided it into 5, each of the width would be like 2 over 5. If divided into 10, each of the width would be 2 over 10. Let's just say n. We divided into n intervals, so 2 over n. So this width right here is 2 over n. Now notice that the heights of the rectangle change, and it changes depending upon where on the curve I am from the 0, which was 4, to the 2, which is 0. So I'm gonna call that the y, okay, or the y of the ith interval. Again, that just is talking about some particular location from 0 to 2. Now I'm going to get fancy here. The function was negative x squared plus 4, and also if I think about it, the first one was 0 over n, and then this was the first one would be, right, the first value here would be 1 over n. No, it'd be 2 over n. Then the next one, because we're dividing, the width is 2 over n, it would be 4 over n. Next one would be 6 over n. And so what would be the ith interval if I is from 0 to n? It would just be 2n over 2ni. Okay, so the first one was 0. The second one, anywhere along the way, would be some multiple of 2n. That's what this is talking about. Okay, so I need to know what my x is as I travel this way. All right, so what is the area of that? Well, everybody knows area is the width times the height. Okay, now remember, what is y sub I? I got to use a formula, so that's going to be 2 over n times my formula, which was what? Negative x squared plus 4. Okay, well, what am I plugging in for my x sub I? Okay, my x sub I is this expression right here. So 2 over n I. Okay, now let's do a little math here. Let's do a little algebra. 2 over n. Let's see, I square that. That's going to be minus 4 over n squared I squared plus 4. Okay, and let's multiply these two out together. I'd have negative 8 over n cubed I squared plus 8 over n. So what this is doing, this is representing the area of that blue rectangle as I travel from the left all the way over here to the right. And we want to see if there's a way for us to use a limiting process to get this 5.33 answer. Okay, so remember this expression right here represents the area of that little rectangle. Now, if we add up all of the rectangles, we should get some expression equivalent to the total area under the curve. So that's what this is. It's just saying, as I start from my first, just having my left rectangle all the way up to my last rectangle, I add up the areas of everybody, I'll get the total area. So that is a summation formula. Now I'm going to do a little algebra here. So I've rewritten it in this particular location here. And there's a couple formulas that you'll learn in calculus. Here's a really neat formula that if you have an expression with that looks just like this, and you have I squared, that is equivalent to this algebraic relationship, and the same thing for some constant. Okay, now you'll go through that and you'll explore that and you'll get that, so that'll be helpful. Okay, now let's go over here and rewrite this. So now our expression is going to be negative 8 over n cubed times n times n plus 1 times 2n plus 1 over 6, and we're going to have to add to that this the constant, which in this last case would be 8 over n times n. All right, now let's do a little algebra here. One of these n's will drop out, so I have n squared. 8 over 6 is 4 over 3. So I'm going to say negative 4 over 3, and then I'm going to multiply this expression out, which is 2n squared plus 3n plus 1, okay? And of course, this is 8 over here. Now, this is going to be, I forgot my n squared here. So when I multiply these two together, I get negative 8 thirds. The n squareds go away. Minus, this is going to be, the 3's will divide out, and so you'll have 4 over n. And then the last one would be minus 4 over 3n squared. Of course, you still have your 8 over here. Now, let's go back. Remember, we were taking a limit of this. What's the limit of this expression as n approaches infinity? Well, you may remember that the limit of 1 over x as n goes to infinity, 1 over x, okay, as x goes to infinity is 0. So the same thing would be true here. You'd have negative 8 over 3 minus 0 plus 8. And now you have 8, which is, what is 8? 8 is 24 over 3, so negative 8 over 3 plus 24 over 3, and that's going to give you 16 over 3, which is 5 1/3. Now, let's pause here for a second. Now, what we did is I showed you the shortcut to get that 5 1/3. I showed you where we actually did the area under the curve, and it did approximate that 5 1/3, which is really very interesting. And so here, let's show that again. Okay, so here you are. We have 5. We have 5 rectangles, and we're trying to make the rectangles thinner and thinner and thinner. So as n goes to infinity, an infinite number of rectangles, this little space over here on the curve will become less and less, and it will approximate the true area under the curve, which again, is very, very interesting. And notice we're at 29 and we have 5.33. So it does work. Now, the point is that you could have any type of phenomena that's related to a function. It could be a square root. It could be a trigonometric function. It really could be a lot of different possibilities, and a lot of things in life can be modeled with some type of math function. Of course, that's an interesting question, why that is true. Some don't, and there's actually a method in calculus for that approximation. But it is very, very interesting. Things in physics, things in other, in the life sciences, using exponential growth and so forth. So these ideas of an infinite amount, a summation of a value, a total of a bunch of little increments, and you being able to use a formula and a procedure to come up with a very easy way to figure out that summation is truly an amazing feat of what mankind has been able to do with mathematics. And you'll see that a lot of applications in calculus for integrals. One would be like area under curve, but another one would be surface area of a strange looking figure or a curved figure, volume, and we could think a lot of possibilities related to volume of objects that have some type of function that directs their curvature. Well, I hope that was interesting, and maybe that gave you a little taste of what calculus is all about.